Hello, Math 1332 students. This is section 2.2 with a little postscript from section 2.1, something I forgot to mention, the definition of equal sets versus equivalent sets. Not really sure why they put that in section 2.1. As you'll see, kind of need the concepts in section 2.2 to really define that. But anyway, let's talk about some examples. So here's a set A with 3 elements in it, A, B, C, and here's another set B with 3 elements in it. So since their cardinalities are the same, we say that they are equivalent or equivalent if you want to change it from the English word, which makes you think of it's the same as the word equal. There's a one-to-one correspondence between the two of them, right? So we call things that have the same cardinalities equivalent. But they are not equal sets. For example, here's a set C. It has 3 things in it: 21 thirds, 48 halves, 27 thirds. You'll notice that it also has 3 elements in it. It has cardinality of 3. So for A, B, and C, they are all equivalent, but only sets B and C are equal, right? Because everything that's in B is also in C, right? 7 is 21 thirds, 48 halves is 24, 27 thirds is 9. So it's not only that they are equal in cardinality, we want to say they are equal. But to really define that concept, we need, So all 3 sets, A, B, and C, have 3 elements in them. Okay, so A, B, and C are all equivalent, but only sets B and C are actually equal. To really prove this, we need to actually define what we mean by set inclusion, which has this notation. So let's take a look over here. Let's see without the glare. Right, great. There we go. Okay. So definition of set inclusion. A, or is a subset of. A is a subset of B if and only if, okay, if and only if it's true that if A, little a belongs to A as a member, element of, then little a also has to belong to B. So for example, the set 1, 7 is a subset of the set 1, 7, 9 because 1 is in this set and 1 is in that set. 7 is in this set A, and it's also in the set on the other side to the right of that symbol. So 1, 7 is a subset of 1, 7, 9. Note, however, that if you look up here, the opposite is not true, right? I'm trying to get rid of the glare on that example. Yeah, right there. So notice that 1, 7 was a subset of 1, 7, 9, but 1, 7, 9, so that was a true statement, but that this is a subset of that is not, because here's 9 on this side, belongs to A, but it does not belong to B. 9 does not belong to 1, 7. Sorry about that. Let's see, some more examples. The set containing 1 is a subset of the set containing 1. Why? Because the number 1 belongs to this set A, and the number 1 belongs to this set B, the one that's to the right of that symbol. Here's an example that's a little hard to swallow. The empty set is a subset of, say, the set 1, 2, 3. If something belongs to this set on the left, then it belongs to the set on the right. The fact that there's nothing that belongs to the set on the left means we're starting with a false premise. And in this case, we will say that this statement is vacuously true. A belongs to the subset, is an element of this set on the left. That's a false premise. It's like pigs could fly. We can say anything after that. So it actually, and we're going to have more about such logic in chapter 3, but here's your first example of it. So in fact, it's a law. For any set S, the statement that the empty set is a subset of that set is a true statement. Vacuously true. Also, something that's not vacuously true is that any set is a subset of itself. Everything that belongs in this set, S, belongs to the set S on the other side. So it satisfies the definition of set inclusion. Okay, now we can define when two sets are actually equal. Okay. When can we write A equals B? A equals B if and only if it's true that A is a subset of B and B is a subset of A. It has to go both ways. Example, B and C over here, you remember, were equal sets. Here's B, 7, 9, 24. 7, 9, 24. And here's C, 7, 24, 9. Remember, order doesn't matter. Inside curly brackets. So everything that's in this set belongs to that set. Everything that's in this set belongs to that set. So that was an example. All right, so that's being more clear about what we were saying at the end of section 2.1. All right, let's look at this set. Let D be the set of all natural numbers such that n is an odd number. 1, 3, 5, 7, 9, 11, ... Let E be the set of all natural numbers that are even. 2, 4, 6, 8, ... You'll notice that 3 belongs to the set D. It's an odd integer, odd natural number. But 3 does not belong to the set E. So these two sets are not equal. The set of odds is not equal to the set of evens. However, if you see page 57, the middle of the page, talks about when two infinite sets are equivalent if they have a one-to-one correspondence. We can make a one-to-one correspondence between the set of all odd numbers and the set of all even ones. So we say that they are equivalent, but they're not equal. Some more examples. Let's see, how far up do I want to go there? That's about right. Those are maybe definitions, a little bit higher. Okay. There's another type of set inclusion called proper set inclusion. If A is a subset of B, but A is not equal to B, it's not all of it, then we say A is a proper subset of B. Proper as in a very exact definition of. There's a couple bits, different ways of writing is a proper subset of B. Most textbooks write this, and you can't see it because of the glare. Most textbooks write this. A is a subset of, but not equal to B. But your book is using A just is with the top half of that, not the lower or equal to possibility. So Blitzer is saying this is the same thing as A is a proper subset of B. Let's look at some examples. Suppose F is the set with two things in it. One of them is the number 1, the other one is the set containing the number 3. And let's say G is just the set containing 1 and 3. You'll notice that F and G are equivalent because they have the same cardinality. There's a one-to-one correspondence between them, but they are not equal. Okay, they are not equal since the set containing 3 is an element of F there it is, inside the set F. But the set containing 3 is not an element of the set G. Inside the set G, you don't see an element, a member that is the set containing 3. Right, so the set containing 3 and 3 are not the same thing. And therefore, these two sets are equivalent but not equal. Here's a concept your book didn't give you, this cute little notation, but it asks you to find out how many things are in it. This is called the power set of A. So that's a fancy script P of A, the power set of A is how you would read that. The set of all subsets of A. That's the definition of the power set. So for example, if A is the set containing 1, 2, 3, then the power set of A is the set of all subsets of A. So for example, the empty set, which is a subset of every set, the singleton set containing 1, the singleton set containing 2, the singleton set containing 3, the set of all pairs, 1, 2, pair 2, 3, and 1, 3, and then finally the whole set A itself. Every set is a subset of itself. So you'll notice that there are 8 things in the power set of A. The number of subsets of the set A is the cardinality of the power set of the set. There's 8 things in there. 1, 2, 3, 4, 5, 6, 7, 8. You'll notice that's equal to 2 to the 3, which is, in this case, 2 raised to the cardinality of the set A. In fact, that's always true. That's another theorem. Let's sort of take one more example of calculating the number of subsets of a set. This last little example here in green. Can you see that? Nope, not yet. All right, way up there. Last little bit. If the set A contains A, B, C, D, small lowercase letters, there's 4 things in there. How many subsets of the set A are there? Same thing as asking what's the cardinality of the power set of A. And by that little rule, that's always equal to 2 raised to the cardinality of the set. This set A has 4 things in it, so the cardinality of its power set is 2 to the 4, or 16. That comes in handy when you're trying to figure out the number of possible subcommittees of a committee. So for example, if you had a committee that had 4 senators in it whose names began with A, B, C, and D, how many possible subcommittees out of that committee could you form? Well, 16 altogether. Of course, the subcommittee that doesn't have anybody in it really wouldn't be called a subcommittee, and nor in that context would the set containing the whole committee be considered a subcommittee. So proper subsets, proper non-empty subsets, proper non-empty subcommittees, 14 of them. We'll get back to that kind of counting problem when we get into chapter 11 on probability. Okay, that's it.